series on complex analysis for undergraduate students. Today's lecture is on evaluation of real improper integrals. We are learning about the use of residue theory in evaluation of real integrals. Today we will learn about the evaluation of improper integrals using residue theory. What is improper integral? The improper integral of a real continuous function f defined over a semi-finite interval, say for example, for positive real line x greater than or equal to 0, is being defined as integral from 0 to infinity of f x dx as limit r approaching to infinity the integral of f x dx on the range 0 to r. So, if this limit is existing for as r is approaching to infinity, we say that this improper integral 0 to infinity f x dx, this is converging, and the value of this integral would be actually the value of the limit on the right side. Now, if the function is continuous for all x on the whole real line, then also we define the improper integral of the type minus infinity to plus infinity of f x dx as the sum of two limits. First, as limit r 1 is approaching to infinity minus r 1 to 0 f x dx plus limit as r 2 is approaching to infinity integral from 0 to r 2 of f x dx. Here both r 1 and r 2 we are taking as positive and both are approaching to infinity. Now, we say that this improper integral would be convergent if both these limits, that is the first one and the second one, both these limits are existing and the value of this improper integral would be sum of these limits. There is one more way in which this improper integral is being defined, and that value assigned to this improper integral is known as the Cauchy principal value. What is it? It is being defined as the Cauchy principal value is being defined of this integral minus infinity to plus infinity f x dx is as limit r is approaching to infinity integral from minus r to plus r f x dx. And we say if the integral minus infinity to plus infinity f x dx, if this is a convergent integral, that is if both these limits are existing, then the Cauchy principal value would be equal to the value of the integral, or in other words we are saying is if this integral is convergent, then the value of this integral is nothing but the Cauchy principal value. What it says is rather than calculating these two limits, we would calculate only this single limit where the integral we are calculating from minus r to plus r f x dx. Now, this what we are saying is that if integral minus infinity to f x dx converges, then integral minus infinity to plus infinity f x dx would be same as principal value of the integral minus infinity to plus infinity f x dx. What is the principal value? Principal value we have just now seen is that this is limit as r is approaching to infinity minus r to plus r f x dx. What it says is that let us just take a very simple example here. The integral we have defined as limit r 1 is approaching to infinity minus r 1 to 0 and limit as r 2 is approaching to infinity 0 to r 2 of the function f x. This is what we have defined this integral. We are saying is if this integral converges, that means both these limits are existing. Then we say that the sum of these limits would be actually this particular limit, limit r is approaching to infinity minus r to plus r f x dx. Now, let us say for one example, if I take simply the function x, that is f x is equal to x, then from here minus r to r x dx, we do know this is x is an odd function. So, it would be 0 for all r, that is the limit would be 0. So, the Cauchy principal value for the function x would be 0. But that is not the value of the integral, because this integral is not existing. Why? If I take the integral from say 0 to r2 of f(x) dx, that would be your r2 square by 2. As r2 is approaching to infinity, it would approach to infinite. Similarly, this one is also going to be approach to infinite. So, what we have just now said is that if f(x) is equal to x, then the Cauchy principal value exists, but none of the integrals, neither this limit is existing nor this limit is existing. So, existence of, we said is that if the result which I had quoted here is, if this integral is convergent, then the integral would be equal to the Cauchy principal value. So, what we are saying is that from this way it is true, but the existence of Cauchy principal value does not say that this integral is convergent, because just now we have got this counter example. Now, can we say in with certain condition that will it happen that if Cauchy principal value is existing, we could say that this integral is convergent, and that is value of course, if it is convergent, then the value of this integral would be the Cauchy principal value. So, we just want to find out under what condition we could say that existence of Cauchy principal value, that is existence of this limit, says is existence of this integral, that is existence of this limit says existence of both of these limits. Let us see. If my function is even, that is if of f of minus x is f of x for all x on the whole real line, then this integral, actually then the Cauchy principal value, if the Cauchy principal value is existing, it would convey that this integral is existing. Why? You see, or this integral is convergent. If f of minus x is f of x for all x, let us see this and if one of this right hand side limit is existing, say suppose this limit is existing for r2 approaching to infinity 0 to r2 f(x) dx. If this limit is existing, if I change x to minus x, I would reach to this interval, this integral. So, if this limit is existing, this limit would also exist. That says is only, and from here what we are getting is, we are saying is Cauchy principal value exists. If this is even and Cauchy principal value exists. Cauchy principal value is limit r is approaching to infinity minus r to r f(x) dx. Now, f(x) is even, we do know that if a function is even from the properties of definite integral, where this r is a finite value, that interval integral from minus a to plus a f(x) dx for x for f being an even function, we could write it as 2 times integral 0 to a f(x) dx. That says is I could write it as 2 times integral 0 to r f(x) dx. And then as r is approaching to infinity, what we are saying is integral as r is approaching to infinity, limit as r is approaching to infinity, integral from 0 to r f(x) dx, that is similar to the second integral, is existing. So, Cauchy principal value is existing for an even function, simply says is that in this definition of improper integral from minus infinity to plus infinity, this second limit, this is existing. Since this is existing and the function is even, we could say that this limit is also existing, since I just change x to minus x and this integral would be converted to this integral, and this limit would be, this whole limit of this integral would be converted to the limit of this integral. So, if it is existing, this would also be existing. What it says is, if Cauchy principal value for an even function is existing, both these limits would be existing. That says is that my improper integral minus infinity to plus infinity f(x) dx would be convergent, and the value of the this integral should be the sum of these two limits. What is these two limits? This limit, if I do see, this is nothing but half of this limit r is approaching to infinity, or that is you could say is half of the Cauchy principal value, and that is same over here. So, sum of them is again the Cauchy principal value. So, now what we have got, that the result which we have got, the one result we have got when we are defining the improper integral on the whole real line from minus infinity to plus infinity, then if the integral of a function is convergent, it would be equal to the Cauchy principal value, where the Cauchy principal value we are defining in this manner. But Cauchy principal, existence of Cauchy principal value does not guarantee the convergence of this improper integral. The other thing which the result which we have got is if my function f is an even function for all x, then the existence of Cauchy principal value says convergence of the improper integral. So, we have got the result that if f is even and Cauchy principal value exists, then the improper integral minus infinity to plus infinity f x dx is convergent, and the integral 0 to infinity f x dx is 1 by 2 or half of integral minus infinity to plus infinity f x dx. So, you see is that is we are using this kind of result many times in our calculation of integrals, but that result is not true for for this improper integral. That result was the property of the definite integral says is here the limits has to be finite, that is minus a to plus a, only then it is 2 times 0 to a f x dx. Now, what we are saying is if the improper integral is convergent, then also then for the improper integral also the same thing would hold true. What it says is now we would go for evaluation of this improper integral, either this kind of improper integral or this kind of improper integral. If the function is even, let us just try when the function is a rational function, that is it is a ratio of two functions and those two functions are also of a special kind. So, let us see, we want to go for the method of evaluating improper integral of rational functions using our residue theory. So, let the function f x is of the form p x upon q x, with p x and q x are both polynomials and q x has no real 0, that is what are the zeros of this, they are all imaginary, and moreover we are having one more condition that p x and q x are such that no factors are common also, that is both the polynomials p x and q x have uncommon factors, and moreover one more assumption on the degree, that is degree of the denominator q is at least 2 degrees higher than the degree of the numerator. So, with these conditions let us just try to evaluate the improper integral minus infinity to plus infinity f x dx. What we will do to apply the residue theory, the improper integral minus infinity to plus infinity f x dx we would change to contour integral f z z z, where f z we would take the corresponding complex function, as the function f x is here, p x upon q x will replace this x by z, that is with the complex variable, and we would take this complex integration, that is the contour integration, with the contour actually being the semicircle in upper half plane. The contour we would take the C is that the semicircle in the upper half plane plus the line x is equal to 0, that is the real axis. So, we will take this semicircle for as the contour C, close contour C, and then we would apply our residue theory in this one. We see if it is we are taking over here, since we had assumed that my f is of the form p x upon q x and q x is having no real 0, that says as if I am replacing my or I am making the corresponding complex function f x as f z, then f z would be of the form p z upon q z. Since q x is not having any real 0, that says is q z would have the 0 on the all the complex ones. Complex zeros means is they would be isolated singularities of the function f z would be either on the, that none of the singularity would be on the real line, they would be either in the upper one or either over on the upper plane or on the lower plane. Now, since we had assumed that this f z and q z both are polynomials, so whatever be the zeros of this polynomials, they would be all these singularities would be isolated singularities, and if any function is having isolated singularities, then certainly they would have a finite number of singularities only. So, if I am taking on the upper half plane, there would be some finite number of isolated singularities only. So, let us take this semicircle of the radius r we are taking large enough such that it is covering all the isolated singularities of this function f z, that is all the isolated singularities of this function f z in the upper half plane, they are interior to this semicircle, which is bounded, which we are bounding by the line x is equal to 0 or the x axis. So, what we would get is, now if I transform my integral minus infinity to plus infinity f x dx. So, now if I see is this f z which is having isolated singularities inside this closed contour, then we do know that for finding out the integral along this contour, we can use the residue theorem. If it is having more than one isolated singularities or one isolated singularity, we could give the integral along this whole contour as sum of 2 pi I times sum of the residues at all those isolated singularities. So, what we are doing it, since it is having zeros, isolated singularities would be zeros of the denominator. So, we do know with our theorem which says relates with the poles with the zeros, that if denominator q z is having zeros, then any function of the form p z upon q z, where at all those, because we have assumed here that both this p x and q x are such that none of the factors are common. That says is none of the zeros of q would be the zeros of p. So, at none of the zeros of q, p z naught will not be 0. That says is the conditions for this that theorem of relation between poles and 0 is satisfied. Hence, f z would have finite many poles in the upper half plane only, and by the residue theorem we could say that the integral along this closed contour C, which is consisting of this half circle and the line x is equal to 0 between minus r to plus r. So, this we are saying is, now I could write it as dividing into two contour integrals. One is only half circle, which I am writing it by s in the counterclock manner, s f z d z, and plus the sum minus r to plus r of f z d z. We see when we are talking about the integral along this real line minus r to plus r f z d z, we do know that this is simply x. So, we do say is that this integral would be actually minus r to plus r f x dx. By residue theorem, it should be same as 2 pi I summation of all the residues, summation of residues of f z, where summation is over all poles in the interior to this upper half plane. Now, what we have to get this integral from minus infinity to plus infinity, the only thing we have to show that limit as r is approaching to infinity. First thing is that this integral will approach to improper integral minus infinity to plus infinity f x dx. Since here what we are having is, we are talking about the residues. Residues are certain finite numbers and the sum of this thing. So, the right hand side would be the finite one. So, when I am putting the limit over here as r is approaching to infinity on both the sides, this side is being a constant, not depending on r, it would be same as this one. Here this would change to the improper integral minus infinity to plus infinity f x dx. And now, what we have to remaining to show is that this improper integral is this minus integral along this contours S of f z d z, where the S is nothing but the half circle or the semicircle. What we have to show that as r is approaching to infinity, rather the plan which we are going to do is, that is, we will show that as r is approaching to infinity, the integral of this function f z along this contour or this semicircle S is approaching to 0. So, let us see that is now what we are, then what we would get is that we could get the improper integral using the residue theory. So, let us see what now we want. We want to show that as r is approaching to infinity, the integral along the contour S f z t z is approaching to 0. S is my semicircle on the upper half plane. Let us see that is what this is. Now, since we are talking about this semicircle, why we want that is because we have taken it, we want minus infinity to plus infinity. So, let us say this semicircle we could parametric representation would be r e to the power I t, where t is ranging from 0 to pi. So, if I take z in the, so first thing is we are making this z in the polar coordinates, and on this semicircle we are having is that z is r times e to the power I t for 0 to t is ranging from 0 to pi, r is fixed one. So, on this semicircle on this contour my z is r e to the power I t with r as fixed one. Now, we want to show, so let us write what is that my this contour integral. Moreover, my f z is of the form p z upon q z. Let us just try to see is that this integral of f z along this contour S is approaching to 0. So, what the method we would use is, we would use our ML inequality. So, you find it out that this ML inequality which we had shown that if my f z could be bounded by some constant, then it is that m, then the absolute value of the integral is always smaller than or equal to m times the length of contour. You see, that is how important that is. We are using it in at so many places to find out the solution of many problems. So, here again what we would find out, first we will find out what is the bound for this f z. That bound we do not have to find out inside this one, because what we have to assume that as r is approaching to infinity. So, we would say that when r is large, that is when r is greater than this fixed value r. So, for all those z for which z are greater than r, that is z is our absolute value of z is greater than r, then we want that is we have to find out its bound. We had assumed that p and q both are polynomials. So, let us see for z greater than r, since p and q are polynomials and degree of p is at degree of q is at least greater than 2 degrees higher than the degree of p. So, let us say p z is suppose of the degree n, and let us say this is a polynomial of the form a n z plus a n minus 1 z to the power n minus 1 and so on. So, we could write p z as we have done in one of our earlier lectures. We could take the z to the power n as common, and we could write our p z as a n plus a n minus 1 upon z plus a n minus 2 upon z square plus a naught upon z to the power n into z to the power n. So, if I take the modulus on both the sides, we do know that mod of p z should be less than or equal to, we do know that mod of x plus y is always less than or equal to mod of x plus mod of y. So, we had applied this one. So, each term we had written here separately. Also, we do know mod of x into y is always equal to mod of x into mod of y. Using that one, we could again separate it. So, finally, what we are getting, that mod of p z would be less than or equal to mod of a n plus mod of a n minus 1 upon mod z plus so on mod of a 1 upon mod of z to the power n minus 1 plus a naught upon mod of z to the power n into mod of z to the power n. Now, so from here what we have got, if z is greater than r, if z is greater than r, we do get 1 upon mod z would be less than 1 upon r. Since this r I am taking this fixed value, some fixed value r naught. So, 1 upon mod z would be less than 1 upon r, 1 upon mod z to the power n minus 1 would be less than 1 upon r to the power n minus 1 and so on. So, what we are getting is each of these terms are bounded by some constant, and what that constant is, that r is very large enough. So, 1 by r would be whatever 1 by r, that would always be larger than 1 upon r to the power n. So, we are getting is that we are being bounded by the functions which are lesser, and so what we could say is that all these terms which are inside this bracket, they are bounded by some constant, say k1. So, we could write this is bounded by k1 times mod z to the power n. Now, let us see the denominator qz. Now, qz again we are saying is that this is a polynomial of degree, let us say p, which is at least 2 degrees higher than degree of pz. So, that says that I should have at least the degree n plus 2. So, let us see then let us call it the polynomial as say b p plus bp plus 1 bp minus 1 z to the power p minus 1 and so on b naught z to the power p b naught. So, again we would be taking in the similar manner this z to the power p common. What we would be writing is, rather than using the inequality that mod of x plus y is less than or equal to mod of x plus mod of y, we would use the inequality that mod of x plus y is greater than or equal to mod of x minus mod of y. So, we would write it as bp, this qz would be greater than or equal to mod of bp minus mod of bp minus 1 upon mod z minus mod of b1 upon mod z to the power p minus 1 minus b naught z upon mod z to the power p into z to the power p. You do find out that is this kind of things we have done in one of our earlier lectures. You can just refer it over there and find it out the details over here. I am explaining here, that is first I have breaked it bp minus all those terms, and then we had used the x plus y is less than or equal to x plus mod of x plus mod of y. That is why we are getting like this one. So, here again when z is greater than r, 1 upon z would be less than 1 upon r. That says is minus 1 upon mod z would be actually greater than minus 1 upon r. So, each of these terms are bounded above by some constants. This is bounded by minus mod of bp minus 1 upon r, this is bounded by minus mod of b1 upon r to the power p minus 1 and so on, and this term is some constant, and what we are having r is some finite number and large number. So, all these terms which are these bounds, they would certainly be some small number. So, we are subtracting and we are taking whatever small or large, we are taking its absolute value. So, that says is this complete absolute value should be bounded above by some constant k2. So, we do write it as this is greater than some k2 times mod of z to the power p. Now, what we have got? We have got that when z is greater than r, my numerator pz is bounded above by k1 times mod z to the power n, and the denominator is bounded below by k2 times mod z to the power p. That says is that I could write if z is less than k1 times mod z to the power n upon k2, because 1 upon qz is bounded above. So, 1 upon qz would be less than or equal to k2 times 1 upon k2 times z to the power mod z to the power p. So, what I am writing k1 upon k2, let us say some other constant k upon mod z square, because at least the difference between these p and n is 2. So, it has to be greater than or equal to 2. So, at least it has to be 2. Now, when z is greater than r, we do know 1 upon mod z to the square would be less than 1 upon r square. So, we say this is less than or equal to k upon r square. Now, we do know as r is approaching to infinity, this k upon r square would approach to 0. Once we have find out that is mod of f z. So, we had find out actually that when z is greater than r, my function f z is bounded by a constant. That is we have find out an upper bound for this function f z for the reason when r is higher, that is for all this z above this one, or what you say is that is we have taken this semicircle and we are trying to take the limit as r is approaching to infinity. So, whenever this we are saying is some fixed r, we are approaching towards, we are going to the higher values. Now, what it says is, it says is that so what now we do have, we had find out that f z absolute value of f z is bounded by k upon r square when mod z is greater than r, and so use the ML inequality for the integral s integral of f z dz on the contour s. Using the ML inequality, this is absolute value is when it is on this r, we are saying is that some r naught we have taken and it is greater than. So, it is k upon r square and into the length of contour L. What is this? Is the semicircle. So, the length of this contour, that is the your perimeter of this semicircle is, we do know, pi times r. So, it is into pi r. So, what we have got that this integral is less than or equal to k times pi upon r. Now, whatever this absolute value, this is always going to be positive. On the right hand side, we have got that this absolute value is less than a constant upon r. What is this r? So, if I take this s is such that the limit r is approaching to infinity, that says is I am increasing my radius of this semicircle. So, as z is becoming greater than r, that is we are reaching out and out, my semicircle is increasing. What I would be getting is that this, since this is bounded by this positive quantity and this positive quantity would go on decreasing, that says is the value of this integral must be 0. So, what it says is it would approach to 0 as r approaches to infinity. This says is now that this integral s f z dz is 0. So, now what we have got? We have got that along this closed contour, the integral of f z dz is by the residue theorem, it is 2 pi I times summation of the all the residues of f z inside interior to this this contour C, and this what is this integral over here, that we had breaked into two parts. One is that contour integral on the semicircle S and another as the contour integral on the line on the real axis minus r to plus r. Now, I am taking this now we are taking this as the limit is approaching. So, what we have got that actually integral minus infinity to plus infinity f x dx would be equal to 2 pi I times summation of residue of f z, where the all the residues we would take at all the isolated singularities inside this semicircle. So, what the method we had actually find it out by this result which we had shown. Actually, we are saying is that if we have to evaluate an improper integral minus infinity to plus infinity of f x dx, where my f x is a rational function, that is it is of the form p x upon q x, where both p and q are polynomials, and the polynomials are such that we do not have, we have to make those polynomials should not have any factors common, that is we are making them as you could say is reduced polynomials which cannot be reduced more further. Moreover, we had assumed one more thing, that the degree of the denominator polynomial must be higher than the degree of the numerator polynomial, and the difference has to be at least 2. then we are saying is that this improper integral we could evaluate using the residue theory, where what we are taking is that all the simple poles, we would take a circle such that all the simple poles are lying inside on the semicircle, and we would talk about only the positive that is on the y positive, that is in the upper half plane only, and there we are calculating the residues, all the residues in the upper half plane only, and we would all the poles in the upper half plane, and we will calculate the residue of the function f z in the upper half plane. Like that we could do. So, let us see that is how we would going to apply it with the help of one example. Say evaluate this integral 0 to infinity 2 x square minus 1 upon x to the power 4 plus 5 x square plus 4 dx. See, we are having my function f x as 2 x square minus 1 upon x to the power 4 plus 5 x square plus 4. This is of the form p x upon q x. P x, this is 2 x square minus 1, this is a polynomial of degree 2. The q x is of the form x to the power 4 plus 5 x square plus 4, this is also a polynomial of degree 4. So, the difference between the degree of p and q is degree of q is 4, degree of p is 2. So, the difference is 2. So, we want that is at least 2. So, it is 2, it is satisfying the conditions of the method just now I had explained. Another condition was that the denominator q should not have any real 0. From here we see is that all the signs are positive. So, certainly it is not going to have, and if I just try to find out the zeros of this x to the power 4 plus 5 x square plus 4, we will not have any real zeros over here. All the roots are the complex numbers over here. Moreover, f of minus x, since it is x square, so it would remain as x square. So, it is 2 x square minus 1, x to the power 4 for minus x, it will remain as x to the power 4, 5 plus 5 times x square, it will remain as such, plus 4. So, it is same as f of minus x is equal to f of x for all x, that is the function is even also. So, that says is we could apply the Cauchy principal value and the second formula, which says is that for using this Cauchy principal value, we could say that integral 0 to infinity 2 x square minus 1 upon x to the power 4 plus 5 x square plus 4 dx should be half of minus infinity to plus infinity integral of this function, same function 2 x square minus 1 upon x to the power 4 plus 5 x square plus 4 should be equal to the 2 pi I. So, half would cancel the 2 pi I times summation of the residues of f z, where f z is the corresponding complex function. So, what will be my f z? Corresponding complex function as 2 z square minus 1 upon z to the power 4 plus 5 z square plus 4. So, what now is remaining to evaluate this integral is that we have to find out the residue of the function f z. So, let us find out the residue of the function f z. Let us see. The function is my 2 z square minus 1 upon z to the power 4 plus 5 z square plus 4. This we could write as z to the power 4 plus 4 z square plus 4. So, or that is the z square plus 4 into z square plus 1. So, the factors we have got from here, if we do see the zeros of the denominator would be z square plus 4 is 0, that z is equal to plus minus 2 I, and z square plus 1 is equal to 0, that is z is equal to plus minus I. That says is this function has 4 simple poles. So, q z is 0 at plus minus I and plus minus 2 I, hence all these zeros are simple zeros. So, f z would have all the simple poles at z is equal to plus minus I and at z is equal to plus minus 2I. Now, we want, that is the our method says is we want the residues at all those poles which are only in upper half plane. So, here if we are having is plus I would be there, minus I would be somewhere here, plus 2I would be here and minus 2I would be somewhere here. So, we want that in the upper half plane we do have only 2 poles, one is at I, another is at 2I. So, you see here in this particular example we are having both the poles are on the imaginary axis. So, let us choose my circle of the radius 3. So, it is covering both these poles. What it says is, now I would have to find out this integral only inside this one, and then we would go ahead because we want the integral from minus infinity to plus infinity. So, we just directly use the formula. This is just I am showing is that, however, if there are for the function is of the form p z upon q z, then it would have a finite number of isolated singularities, and since it is of the form the q and p are the polynomials, it will have all the poles, and all those poles we could find out are such that all the poles would lie interior to the semicircle bounded by the real line. So, let us find out the for using that formula we have to find out the residue at plus I and plus 2I. So, first residue at I, we would use the simple first formula of finding out the residue, which says is residue at z is equal to z naught of any function f z is limit as z is approaching to z naught, z minus z naught of f z. So, here my point is isolated singularity is at I. So, residue at z is equal to I of f z would be limit as z is approaching to I, z minus I times f z. This we could write as f z 2 z square minus 1 upon z square plus 4 into z square plus 1. This z square plus 1 we could write as z plus I and z minus I. So, when we are multiplying it by z minus I, we would get it as 2 z square minus 1 upon z plus I into z square plus 4, limit as z is approaching to I. That says is evaluate this function at z is equal to I. If I am evaluating at z is equal to I would get z square is equal to minus 1. So, it would be minus 2 and minus 1, that is minus 3. My numerator would be minus 3. See the denominator. At z is equal to I, this term would be 2I. At z is equal to I, z square is minus 1. So, minus 1 plus 4 would be 3. So, we are getting 3 into 2, that is 6I, while in the numerator we are getting is minus 3. So, we are getting is minus 1 upon 2I, that we could write as I by minus I by 2. So, we have got it minus I by 2. Now, residue at z is equal to 2I. Limit as again using the same formula, residue at z is equal to 2I of f z, we could find out as the limit z is approaching to 2I, z minus 2I into f z. So, now we would write this function, the term z square plus 4 we would break as z square plus 2I into z square, z plus 2I into z minus 2I. So, what we would get the function, remaining function when we are multiplying it by z minus 2I as 2z square minus 1 upon z plus 2I into z square plus 1, and find out the limit as z is approaching to 2I. So, that says is just we have to evaluate this function at z is equal to 2I. When z is equal to 2I, z square would be minus 4. So, we would get here minus 8 and minus 1, that is minus 9. Z is equal to 2I, this term would be 4I. Here z square is minus 4, minus 4 plus 3 is minus 3. So, minus 9 minus 3 would get 3 upon 4I. So, what we are getting is minus 3I upon 4. Now, let us find out use that Cauchy principal value formula. So, the integral 0 to infinity 2x square minus 1 upon x to the power 4 plus 5x square plus 4 dx could be given as, the formula says pi I times the sum of all the residues which are in the upper half plane. We have got the two residue in the upper half, two poles in the upper half plane, both are simple poles. We had calculated the residue over there is I by 2 and 3 I by 4. So, we do get it pi I times minus 3 I by 4 minus I by 2, that is pi by 4. So, this is plus I by 2. So, it is pi by 4. So, we have got evaluated this integral using the residue theory. Let us do one more example. Evaluate the integral 0 to infinity 1 upon x to the power 4 plus 1. Again we are going to use the same method. Why? You see the function 1 upon x to the power 4 plus 1, we could write it again as of the p x and q x, where this numerator is constant. Constant can also be treated as polynomial of degree 0, and denominator is certainly a polynomial x to the power 4 plus 1. Since its degree is 0, its degree is 4. So, we do satisfy the condition that the denominator should have degree at least 2 higher than the numerator. Moreover, there is no term which is common to each other. Moreover, the x to the power 4 plus 1 does not have any real zeros, and we do have that f of minus x is same as f x for all x. So, again the formula for Cauchy principal value Cauchy principal value formula would be applicable, and the method just now we have described that is applicable. For that we require a corresponding complex function. So, the corresponding complex function would be 1 upon z to the power 4 plus 1. Hence, using this Cauchy principal value formula, we do know that integral 0 to infinity 1 upon x to the power 4 plus 1 dx would be half of integral minus infinity to plus infinity 1 upon x to the power 4 plus 1, which is half of half times 2 pi I into sum of residues of f z. So, that is pi I times sum of residues of f z. So, now the work which is remaining to do is to find out the residues of f z. My function is 1 upon z to the power 4 plus 1. Its singularities would be where the denominator polynomial z to the power 4 plus 1 has zeros. Now, z to the power 4 plus 1 would be 0 when z to the power 4 is minus 1. Minus 1 we do know, we could write it as e to the power 2 n plus 1 pi I. So, here I am writing it is e to the power I 2 n plus 1 pi. From here we do get for all n 0, 1, 2 and so on. So, from here what we are getting, that z would be e to the power I times 2 n plus 1 pi by 4. Now, let us find out that is what are these zeros are. They would be the poles of function f z. When n is equal to 0, we will have e to the power I pi by 4. Moreover, it is actually it is plus minus, you could have minus sign also, that is also even then it is true. So, with n is equal to 0, we would have the two roots or rather you could say two poles at I pi by 4 and at minus I pi by 4. At n is equal to 1, we would get it 3. So, what we would get e to the power I 3 pi by 4 and with the minus sign e to the power minus I 3 pi by 4. Then if I take n is equal to 2, I would get 5 pi by 4. 5 pi by 4 means is I am getting is 2 pi plus pi by 4. And if we do talk about, because here if I am writing in this manner, that is 1 as e to the power I 2 n plus 1 pi, it says is I am using the polar coordinates. What it says is that if I am increasing my n values, I would be actually unless until I am changing my r, I would be on the same path I am making it, since it is the polynomial of the degree 4, it will have only 4 zeros. So, those 4 zeros we are having e to the power pi by 4, e to the power minus I pi by 4, e to the power 3 pi by 4, e to the power minus 3 pi by 4. Thus, my f z would have, and all these zeros are simple zeros. So, my f z would have simple poles at these points. Let us see what are these points. If I make this as unit circle, then the points are, this is pi by 4, e to the power I pi by 4 means is this is the point pi by 4, this is the point your 3 pi by 4, this is the point minus pi by 4 e to the power minus I pi by 4, and this is the point e to the power minus I 3 pi by 4. So, from here if we see, we are getting only 2 poles in the upper half plane. So, we are having for this function f z, we are having 2 poles in the upper half plane. So, now if when we are going to use this Cauchy principal value formula, we want the residue only at the 2 points, 2 poles, e to the power I pi by 4 and e to the power I 3 pi by 4. Again we would use the formula that residue at z is equal to z naught is p z upon q dash z naught. Because here p z is a constant, so we do not require actually to evaluate p z at different values of z naught. The only thing is that q dash z naught that we have to find out. Since we are having here q z as z to the power 4 plus 1. So, q dash z is 4 z cube. So, actually we had got a simple formula for residue of z is equal to z naught as 1 upon 4 z naught cube. So, let us find it out at both the points, that is e to the power I pi by 4 and e to the power I 3 pi by 4. So, residue at e to the power I pi by 4 would be 1 upon 4 times e to the power I pi by 4 cube, that is e to the power I 3 pi by 4, or in other words we could write 1 upon 4 times e to the power minus I 3 pi by 4. Similarly, the residue at z is equal to e to the power I 3 pi by 4, from here it would be 1 upon 4 e to the power I 9 pi by 4 or 1 by 4 times e to the power minus I 9 pi by 4. So, the residues at both the poles we had calculated. So, using that our formula that integral this is equal to pi I times the sum of residues at all the poles on the upper half plane. We have got the 2 poles, both are simple poles, we had calculated the residues over there, add it up, pi I upon 4 e to the power minus I 3 pi by 4 plus I e to the power minus I 9 pi by 4. Now, we are going to use our Euler's formula for e to the power I theta is cos theta plus I sin theta. What it says is this pi I by 4 is as such, this thing we could write cos 3 pi by 4 minus I times sin 3 pi by 4 plus cos 9 pi by 4 minus I sin 9 pi by 4. Now, evaluate this. Cos 3 pi by 4 means this ray, this angle is your 3 pi by 4, and we do know the cos 3 pi by 4 has value minus 1 by root 2, while sin 3 pi by 4 does has value 1 upon square root 2. So, here what we would get 1 minus 1 by root 2 minus I by root 2. Cos 9 pi by 4, 9 pi by 4 means is 2 pi plus we are getting it again to pi by 4, that is this angle. So, we do know is that cos 2 pi plus theta is cos theta, sin 2 pi plus theta is sin theta. So, we are getting is it is same as cos pi by 4 and sin pi by 4. Cos pi by 4 we do know is 1 by root 2, sin pi by 4 is also 1 by root 2. So, here what we would get, here we have got minus 1 by root 2 minus I by root 2, Here we will get plus 1 by root 2 minus I by root 2, 1 by root 2 plus sign and minus sign, that would cancel it out. I would get minus I by root 2 minus I by root 2. That says is we would be getting is minus 2 I upon root 2. Just multiply it I into I, that is I square is minus 1, we would be getting it as pi upon 2 root 2. So, we have evaluated this integral 0 to infinity 1 upon x to the power 4 plus 1 dx as pi upon 2 root 2. We have today learned to evaluate the improper integrals of the form 0 to infinity of f x dx or integral of minus infinity to plus infinity of f x dx. Actually, what we have learned is that is if f x is a rational function, that is if it is ratio of two polynomials, that says is and moreover we have talked about the polynomials such that the degree of denominator is at least 2 degrees higher than the degree of the numerator. In that case, we said integral of minus infinity to plus infinity f x dx can be given as the 2 pi I times sum of all residues, where the summation is at all the poles which are in the upper half plane of the xy plane or the z plane. We were able to evaluate the integrals of the form 0 to infinity f x dx only for the functions which are even, that is f x is same as f of minus x for all x. So, we had learned one method of evaluation of improper integral, and we had seen that is how this residue theory we can apply over here. So, the theory was a little bit involved, where we have to show that the limit as it is on the semicircle is approaching to 0 as we are making this r to be large enough, and we are from there we are obtaining this one, but the formula which we have got, that was much simpler, or it is actually making us much simpler to calculate the integrals just by calculating the residues and then applying this residue theory. We will learn some more improper integrals. So, this is all for today's lecture. Thank you.